All right, good. Okay, so the technical stuff is done now. Great. So it's really a pleasure to be here today. And so the Wabi team has spent an uncountable amount of hours into trying to put together a very comprehensive view of self-driving. And in particular, what we intended to do is really to bring a very unbiased view of the entire ecosystem. Okay, so I'm going to have a few Wabi slides for you here because it's very exciting. So I can't resist. And then after those few slides, everything is going to be yes, general self-driving. And the idea is going to be to really focus on almost every single component that you need to really, ace in order to really be able to solve this problem. And actually, oftentimes self-driving people think about autonomy, right? Perception, prediction, motion planning as the only thing, but that's actually a tiny piece of the entire puzzle. So what you will see today is that it's a much more complex system. And as you are developing this technology, you need to think about how you're doing the entire thing in a way that is compatible, is efficient, is effective, etc. So the idea is no matter whether you are already an expert in self-driving, but maybe you are focusing on some parts of the stack, or whether you're a novice, today you should be able to have at the end of the tutorial, a very good understanding of where we are, what are the challenges, what are the approaches that people have been looking at. It's a lot about the intuitions of why people have been doing these things, and you should be ready to, do a PhD in self-driving, join a company in self-driving, or whatever it is that you want to do with this really, really exciting field. And I say really, really exciting because, the revolution of self-driving is yet to happen. Right. One day, very, very soon, you're going to look around and, the world is going to be full of, robots. And, the next couple of years are going to be fundamental in this transformation. And in particular with the way that the field of AI is evolving over time right now, is really a great time to get on board with this field. All right. Now, but you need to join sort of like a 2.0 version of self-driving. All right, so without further ado, I guess I didn't say who I am. So I'm Raquel Ertazen. I'm the CEO and founder of Wabi, a very exciting self-driving company focusing on self-driving trucks. And the reason why we are doing trucks is that probably all of you have seen or have been, strangled at home during the pandemic, right? And it was extremely hard to actually get goods, from toilet paper in Canada. I don't know if it was the same everywhere too, anything that you can think of, right? I bought a car during the pandemic. It took me a year to get it. So it was, a very good motivation in terms of, it's affecting every one of us. It's affecting, the entire ecosystem, the entire economy. So let's try to build self-driving to really solve this once and for all. It turns out that it's also a great, kind of use case for autonomy because you drive mostly on highways and the economics work much better. So everything together was, the reason why we are actually doing trucks. So let me show you what we're actually doing. And hopefully this plays.
The future of trucking is autonomous. That means safer roads, a stronger supply chain, a new era of logistics. At Wabi, we believe that to unlock this new era, we need to build the next generation of technology. Meet the Wabi driver. Powered by our AI-first approach, the Wabi.
So this is actually our real trucks.
Let's take a closer look. The Wabi driver has two components: the advanced virtual driver as software, together with sensors and compute as hardware. It includes LiDAR, cameras, and radars for increased redundancy and safety. At its core, the Wabi driver is a full autonomy stack. From sensing the world to decision-making, the entire system as a whole automatically learns from data. Thanks to Wabi World, our groundbreaking simulator, we're able to expose the Wabi driver to the vast diversity of experiences needed to hone its driving skills, which would be impossible otherwise. This makes it safer and smarter before the wheels even start turning. The Wabi driver is a single AI system that is both modular and interpretable, which means we can trace every choice it makes and we can validate its decisions. The Wabi driver has superior generalization capabilities. It can apply learned skills to new situations and geographies it has never seen before, unlocking new autonomous routes with unprecedented speed. We built the Wabi driver with production intent from day one. It's designed to be easily integrated on the assembly line for a safe, reliable, and scalable product. And it's highly flexible, adaptable to multiple redundant truck platforms and sensor configurations. We are unveiling a new paradigm, safe, scalable, and ready for the road. The future of trucking is autonomous. The future of trucking is here.
Cool. So this is what we have been doing over the past 2 years since I started the company. And, it's very exciting. You can actually, thanks, Andre. You can actually see our trucks driving autonomously in an undisclosed location in the States, soon to be disclosed. Great. So let's talk a little bit in terms of, what are the things that you need to do, or how does, almost every single self-driving system work. And I'm going to be focusing a lot in autonomy this part of the year right now. So typically, the first thing that you have, right, is that you're going to collect the information from all the sensors that you have in your self-driving vehicle. And a self-driving vehicle, as you will see in the next part of the tutorial, has many, many different sensors, right? From lidar, cameras, radars, ultrasonics, microphones, you name it, right? There is many, many sources that actually have different frequencies. So there is actually quite a bit of complexity in terms of handling the data and processing that data as it comes. So typically, most of the self-driving vehicles, what they will do is they will localize the vehicle with precision of a few centimeters. And the reason for this is that typically we build, offline high definition maps that represent a lot of the information about the environment. And this is something that, is a very good source of information, but you need to utilize the map as a sensor in the sense that the map might be wrong because maybe the environment might change, maybe there is construction, etc. So you need to be robust to potential changes or detect those changes in your map. So also the map enables you to see much farther than typically the sensors do. So you can actually plan long-term maneuvers, for example. So once you localize, then you need to perceive the world around you. And that's typically, what we call perception, which, is actually, when you go deeper into a software stack, it's much more complex than just high-perform object detection, as you will see in academia in some of the papers, right? But you want to understand everything that is in the scene. And for this understanding, it's not just about the typical categories of interest of vehicles, pedestrians, etc., but it's also about all the potential unknowns and things that you might see on the road. It's a pretty complex task. Then the next bit, and I guess my animations are not working, but the next thing that you need to do is you need to predict what the different actors in the scene are actually going to do in the next few seconds. And why is this important is that if you only focus on the present, you're going to have an extremely reactive planner that might get in trouble. For example, if you're actually working on trucking, a truck takes a long time to actually perform a maneuver. It's not very agile, as you can understand, particularly when you have a huge load, on the back. So you need to be able to do, planning at long horizons. And for this, it's very important that you understand potentially how the future might unroll so that you don't get in trouble with the maneuver that you initiate. So prediction is actually really a very, very important component of self-driving. It's a pretty hard task, as you will see today. All right, so once you know how the world was in the past, is in the present, and then you kind of have an understanding of potentially how the future is, then the next thing that you need to do is to plan a safe maneuver, right? So there is many types of planners out there, but the most important thing that you need to do is always plan a safe maneuver. So safety is the number one thing that you shouldn't compromise. Obviously, there is other things that are important, like for example, you want to make sure that you drive comfortably, particularly if you have passengers that you're driving, right? With goods, it's a little bit less important. You also need to go towards the goal. Right, you might be very safe if you're stopped, but you're not actually doing what you're supposed to be doing. Right, you need to still, carry goods or passengers from point A to point B. Right, so there is always a compromise between these different things, but it's very, very important that safety is the number one priority of your motion planner. And the last bit we decided to talk about is control, where basically, every time that you plan a maneuver and then you actually send the command to the vehicle and you execute it, what it executes is a bit different from what you intended to do, because you don't have the perfect vehicle dynamics, because you don't have the perfect understanding of the friction coefficients or things like this of your environment, maybe the slope, etc. Right? So it's very important that you actually control a super high frequency so that you always bring the vehicle to the maneuver that you intended to execute in the first place. And oftentimes control systems are actually kind of blind. They just try to track a trajectory, which is the motion planning trajectory. And Abbas, in the motion planning and control part of the tutorial, is going to tell you a lot about how this actually works in practice. Okay. And so typically this is something that you repeat at a fraction of a second, the entire from sensors all the way to control. Okay. Typical stack might actually do this at a frequency of 100, 200, 300, whatever milliseconds, right? But every time that you get an observation, you need to repeat this maneuver, this set of models that you have. All right, so as you see, even the autonomy system is a fairly complex problem to solve. And when you look out there, right, is that there is not that many or at all actually scalable solutions that actually have solved self-driving at the scale. And you probably are all thinking, we started I guess a couple of decades ago on this, right? But as a community in self-driving, but definitely there's been tremendous emphasis since the DARPA challenge, right? With industry playing a fundamental role in pushing this technology. But when you look at where we are today, right, commercialization is not there, right? You're probably thinking like, why is that the case? Well, it turns out that, you can, put your statistics hat and then think about, what is the problem that you're intending to solve. So it turns out that the task of driving, right, most of driving is relatively easy, right, in terms of, you're following the lane, etc. But there is many situations that are very infrequent. And that's what makes actually driving really, really hard. Because once some detail of that long tail is actually, quite a significant amount of time that you see things on the road that are actually pretty hard to handle. And this is, this is some examples. Actually, the bottom right is a picture I took in Toronto. I found it fascinating that somebody actually had painted metallic, whatever, their car. So I don't know how that's actually, allowed. It turns out that this kind of thing is not allowed in Europe, but in North America, everything is kind of allowed. So that's pretty dangerous for any camera-based system like a Tesla, right, where everything is reflective. So suddenly the world is going to be very different. You're going to be fooled. The house that you see on the top right, so it's not this picture, but the first time that we went and drove on the real world in autonomy, that's what we saw next to us, a whole bunch of trucks carrying houses. And that was our first time in autonomy, right? Have you ever seen this before in your life? Probably not. But, what are the odds that, in our first test and suddenly there is all these, crazy things, right? So that's why I'm saying that long tail is so long and it's so big that, it's not that rare to see all these crazy things. It's every specific one that is very, very rare, right? All right. So that makes life difficult. And it makes life difficult in two ways. First, you need to make an autonomy system that actually is able to generalize to all these scenarios. So that's hard, right? For those of you that work on perception, prediction, motion planning, whatever, that, handling, many situations, generalization is always a challenge for many machine learning-based systems or rule-based systems, right? Let's not forget that those also don't generalize well. But the other bit that makes this difficult is because when you want to make your safety case where you want to deploy in the real world, you need to prove that your system is safe, which means that you need to test in a lot of these rare situations. And if you use a system that is based on just driving on the real world, you're going to need to drive many miles, millions, billions to see these things, right? So suddenly it becomes a challenge as operationally, and, you're going to spend, hundreds of millions, if not more, right, billions into doing just this test to prove your safety case. So that doesn't seem to be scalable either, right? So these are the two, it's not just about the autonomy, but it's also about the way that you test, you develop, because you can't see this all the time. All right, so if you look at what traditional software stacks and still most of the industry-based software stacks, the way that they look like is something like this, where basically what you will see is that, they are very modular. And this has the advantage that they're also interpretable. But as you see, there is kind of a cascade of modules over here. And that's actually pretty dangerous in general. Why is this the case? Because you're going to have narrow interfaces between these different models. And this means that you're going to propagate little information between them. So if everything goes well and every one of your models is perfect, so long as you actually still have all the information necessary for the next model, you are good. But that's not how the world looks like, right? Or how things happen in reality, because there is going to be uncertainty. You're going to have occlusions. You're going to see all sorts of things where, your previous model might actually struggle a little bit, but struggling a bit is going to result in potentially a chain of mistakes that is going to be, end up with a safety critical situation at the end of it. So that's actually something that, in my opinion, has been a problem of the industry, in the sense that, I always talk about this as it's a software stack built by humans for humans, so that you can understand and agree on the interfaces, but you actually lost most of the information that you have. So that's problematic. And the other thing is that, every one of these models is actually overly complicated. So typically what you will see is that, in order to reason about something, there is a module about it, or there is an explicit variable or something that tells you that, okay, this is pedestrian, this is something else, right? This is the way that I behave if this happens versus that other thing happen. So you need to explicitly create these models, and then you end up with an overly complicated software stack, right? And as a consequence, you end up having, thousands of engineers working on this problem, right? So that's actually one of the reasons also why the industry has spent, typically billions of dollars these days per year as burn rate to continue developing the technology, right? So that's a lot of money. All right, so this is something that we need to go beyond past this, and do something also, like if you have these modular approaches, right? One of the things also that is quite interesting is that, let's say that you are working in perception, you really care about the detection. And let's say that you build this detector that suddenly your AP metrics, or, the way that you measure it is much better. So oftentimes that doesn't reflect into a better driving, because there is little correlation between, this task and the end task. One way to think about it is that certain mistakes are really, really bad and critical, and certain mistakes do not matter at all, right? If you're never going to interact with a particular object, whether you miss it is not really going to influence how you are driving. But a certain, if you are just a little bit off with your detection, and suddenly you think that somebody is going to encroach in your lane, you're going to slam on the brakes, and when you have a truck, that can be catastrophic, right? So that's what tells you that, loss functions are not symmetric. Now in academia, everything mostly is symmetric, so that's actually a bad way to actually measure performance. So it's important to think about how we can build systems where we can really optimize for the tasks that we care about. So the first kind of like way that people were thinking of how to move from this modular system to something where you optimize for the end task was something that looked like this. And we've seen some systems, many years ago, for example, by NVIDIA, etc., where the idea is that I'm going to have this magic neural net, whatever it is, right? And it's going to solve all the problems for me. So long as I give enough training data and enough compute, right, hopefully can generalize to everything, right? So that's a very hopeful approach in many ways, right? But it's actually not something that, for example, for a safety critical application, is going to be a solution. And why is this? Because you need to validate and verify this technology. So interpretability turns out to be extremely important. Let's say that, for example, you go on the road and with an approach of this form, and then you end up having an accident. What happens is that the regulators, the NHTSAs of the world, are going to ask you, why did the system fail? And you can't just say, well, my neural network predicted this thing. And, I see these activations and, they look cool and maybe, right? So that's not going to be a way to explain them, like why your system failed. You need to be able to say the system was thinking this. So interpretability is very, very important. And for those of you that have maybe a system engineering background, you know that validation verification, VMV, is very important to decompose so that you can actually validate and verify this tremendously complex system by validating subsystems and then the system level, okay, in a way that is actually not exponential in the number of all these possible dimensions. All right. So that's why this is also not a great solution. So we have been building over the past, you know, many years. You've seen, I guess, in previous conferences and whatnot. Before we were Wabi, I guess we developed many of these kind of approaches. And then at Wabi, what we did was really to push this to the next level in terms of building an autonomy stack that is end-to-end trainable, but at the same time is interpretable, that generalizes really well, and that is also safety aware. So you have all these different components that you need in order to really build a system that you can deploy and drive on the real world. All right, so it's going to be, I guess, as I said, end-to-end trainable, so that you know, all your models are adjusted for the end task, the task of driving. So now, you know, every time that you make a change, right, actually you will do better in what you care about, and it's going to be, you know, pretty scalable. You can do this with much less people, much faster. All right, and the other bit is about, you know, how do you address the second problem of the industry, which is that things are very rare. You need to test, right? So we build a very, you know, next generation high fidelity simulator, which we unveil a big chunk of what we call Wabi work here at CVPR. And you will see, we'll be giving a couple of talks today, but also during the sessions, you will see some of the technology during CVPR. All right, so the idea is that instead of doing all this real world testing, we invert the pyramid where you do mostly simulation, right? And then you build basically, the simulator really can tell you a lot of information about the performance of the system. So you can mostly develop in simulation, right? And it's mostly validation, verification what you do in the real world. And then you validate and verify not only the autonomy system, but you also need to validate and verify the simulator. And this is a way that is, you know, totally opposite in terms of what the industry has been doing, which has been always about, let's build a prototype, let's get on the road and let's iterate, which is, you know, not the safest solution, not very sustainable and very, very expensive, right? And then we have flipped this around, but the first thing that we did was build this massive simulator. And then that will, you know, it really enable us to build everything else in a much more, you know, cost-effective manner and much safer. All right, so as I said, Wabi World is really our simulator, right? And what you see over here is that, you know, is built with in a very, very, I would say, a very simple intuition, which is if you want to build a simulator of the real world, the simplest thing that you can do is actually clone the world. And then, right, because we see it, right? So if you can clone it automatically, you actually have all the diversity and you can have the high fidelity, and then you can create simulations that are controllable. So you can modify that real world to create new things. And if you do this in a way that is closed loop, so that you're driving with your autonomy stack, then suddenly you can do something that is the same as driving in the real world, but on the simulator. And there was, you know, a lot of thought and technology that went into how you do this in a way that is efficient, that is diverse, that is controllable, and that is super, super high fidelity, where the domain gap is very, very, very tiny in terms of what we have over here. Okay. Cool. All right. So, oh, interesting. I guess we have some music. And this is my last slide about Wabi, which is just some publicity about our simulator that you can see, as I say, today we'll be giving a couple of talks. And I think the session is on Tuesday. I think it's on Tuesday, where you can see Unisim, which empowers a lot of our camera and LiDAR simulation. Cool. All right. So with that said, so that's, I said I will have a few slides about Wabi. That's it. Okay. The rest of the tutorial is going to be about just the field in general. And this is sort of the, the different sessions that you're going to have today. And as I said, we try to be super, super comprehensive. We added, so we did a couple of these tutorials before, and we added also a new system, a new part of the tutorial in system safety validation and verification, because we think that this community should actually understand and learn about this so that you can build the rest of whatever it is that you're interested in, that actually is validated. You can validate and verify so that your technology, your new algorithm, your new cool stuff can actually be deployed on a real world system. Okay. All right. So yes, very quickly going into what you're going to see in every one of these sessions. So the first session, Andre is going to be talking about hardware and sensors. And, there is very different approaches in terms of the sensors that you see in the industry, right? From some companies that want to use only cameras, some of the reasons because they might have already a large set of vehicles on the road, so they have to be very, very careful in terms of the cost of their hardware. Some folks go for a multi-sensor approach where you have lidars, you have cameras, you have radars, etc. So we will just cover a little bit in terms of what are the choices and what are the advantages or disadvantages of those sensors. The last bit of hardware that is also very important is that you need to think about the compute, right? I mentioned before how an autonomy system works, and there was a lot of stuff that you need to do in a fraction of a second, right? So the way that you choose your compute is actually extremely important because all the computation is on the edge, is on the vehicle. Right, it's not on a server somewhere else. And the reason why is actually safety, because if there is no connection, you still need to drive and you still need to be able to be safe on the real world. Okay, so Andre will cover these two bits. Then we're going to go over perception, right? We will go over autonomy. So once you know, okay, you have a truck that is equipped, is integrated with our sensors and compute, how can I use this, right? So the first bit will be about, how can you do perceive the world? And then we will be looking at things such as focus on metrics in terms of how do we measure, performance, but more importantly, since we have, all these different sensor modalities, how can we exploit them such that we have, a very robust, better than humans view of the environment, right? As humans, we actually do saccades. We have, a pretty narrow field of view. Machines have the ability to see much more. Right. The question is about how if we can extract the right information to actually drive safer than humans. But in theory, they see much, much better than humans. We will also be looking at, what are good representations for understanding the 3D world, right? Also, we will be looking at how to do this in a way that is efficient, right? And that's important because don't forget that we need to be on the edge working in real time on a vehicle, right? And the last bit is, about not just categories of interest, right? But I mentioned before that you also need to reason about, unknown objects, things that you don't know what they are. And they happen quite a bit, right? Debris, mattresses that, fell off the truck. I have seen twice in my life, actually, mattresses. I don't know, you guys, and I don't really drive that much or go on a vehicle that much, right? So these things, you need to be able to handle, all those things that you don't necessarily know what they are. All right. So once we kind of understand and how to perceive the world, the next bit will be about motion forecasting. And what you're going to see in the tutorial is we will go over the different motion forecasting, which is in the industry called prediction, over the different paradigms. And it's unfortunate, the name prediction, because if you're a machine learning person, you're predicting all the time, no matter what the task is, right? So that's why we prefer to call it motion forecasting, but maybe there is some prediction that slips into some of our slides. And then we will be looking at things like learning rich representations of the past, of the different information that you have, as well as how you can handle things like interactions, for example, between all the different agents, between the agents on the map, so that you can actually predict better representations. We will also be looking at what are good representations for prediction, right, in terms of the output representations, whether they are trajectories, whether they are things like instance-free, occupancy maps that are very, very popular these days. And there is some cool new way that we have that we unveil also the CVPR with implicit representations that are, in my opinion, a really much better way to look at the prediction problem that is motion planning aware, so that you can do super, super efficient computation without needing to quantize in an instance-free approach. All right, so then Abbas, so Sergio will be talking about motion forecasting, and then Abbas is going to be talking about motion planning and control, and we will go over different choices in terms of representations, the architecture that you can have, the types of planners, whether it's sampling-based planner versus straight up feed-forward planners, etc., and looking at things like how to be proactive versus reactive in the planner. Interpretability will be also touched upon, and then Abbas will be covering things like control so that you actually get a sense of the entire autonomy system. This is one of my favorite topics. We don't see as much of this because self-driving is not at the scale yet. But vehicle-to-vehicle communication and vehicle-to-X, so into infrastructure communication, one day in the future will be very important. And you can look at how you can so there's like two ways or two things that you need to do, right? You need to be able to send very useful information, but also that information should be very compressed, because suddenly it's not that you have 6G or whatever it is, and with many vehicles in the world, right? So you should there is a lot of really interesting technology in terms of how can I do this so that I get the best of both worlds. Every vehicle can send the information about how they are understanding the scene, what they're going to be doing, and you can utilize the information from all the vehicles that you can receive to actually be much safer. And this will be something that if you roll out 10 years into the future, I bet you there is more and more of this. All right, then, so Siva is gonna be presenting, talking about vehicle-to-vehicle communication, and then we're also going to be talking about a lot of the ways that you can build maps, as well as localize those maps. And for these two sessions, then Andre will be covering them. And typically, in self-driving, the way that it works is that, level 5, which is driving everywhere, is a dream, right? So most of the companies have this notion of there is an operation domain, which is a subset of the world where you're intended to operate, that you can characterize well. And basically, given that operation domain that you have selected, you send a fleet of vehicles to collect data, and then from that, you're going to build these really nice three-dimensional maps that are not just geometry, but also you have semantics. So Andre will touch upon how you can actually build these maps from both a 3D-dimensional representation as well as those semantics in a way that is scalable. And there's a lot of really cool technology that go into doing things like this. All right. Then once you have the map right on vehicle in real time, you need to localize with very, very high frequency. And that's kind of the next bit of what the tutorial will be talking about. And Andre will touch upon the online localization on the vehicle, as well as the offline localization that you might want to use in, for example, when you are building the first your maps in the first place. So this mapping and localization is actually really, really intertwined in many ways. All right, then if I manage to get on time from my workshop talk, I will be talking about this session. So let's hope that works with the schedule. But the idea is that data is extremely important in self-driving, right? It's very important for training systems. It's very important for testing the systems. And typically, the industry doesn't necessarily share a lot of information about how this is done. So here we wanted to open a little bit of this magic black box and share with you some of the perhaps open questions or things that you need to take into account when you are actually thinking of data capture as well as evaluation, right? Oftentimes when you're working in academia, what you have is a data set that somebody gave you, right? For example, maybe your kitty or something else, right? And then that's given to you with the tests, the metrics, and then you just work on that problem, right? When you are in industry, it's different because you have the choice to create your data, your different sets in terms of depending on what you're trying to test. So it's very, very important that you have the right information. So we will be looking at, for example, data set curation, which is, vehicles typically drive a lot, right? You're not going to use everything and label everything. That's actually really, really expensive. Maybe that's for the Waymos of the world, but definitely, for us, that we are very, very obsessed with efficiency. This is not something that we do. Instead, we look at, are there ways to characterize when data is interesting in a way that we can also cover the space of things, situations, scenarios that might arise in the world, and we can improve our models. Okay, so I will be talking a little bit about how to think about this and maybe techniques or things that can help you to define your algorithms for doing something like this. There is a growing interest in data sets. I will not go in details on the industry or all the data sets that you have today. We have a slide for you with all the data sets, so you can go and crowd all those different data sets if you're interested in. But I think it's more interesting to look at, as I said, how do you build data in the first place, and then finally, evaluation will also be an important component of this. All right, so from there is a natural transition to how you evaluate in a better way than just evaluating on static data sets. And what I mean by static is obviously there is a self-driving vehicle that has driven and whatnot, right, or a human, and then you're comparing things. But that open loop kind of metric evaluation doesn't correlate well with how well your vehicle drives at all once your system is reasonable. Right, so closed loop evaluation becomes extremely important. I showed you Wabi World before, right? This cool simulator. So today, what we will be talking about, and Siva will be covering, is what are the different, as well as Kelvin, what are the different elements when you're building a simulator that you need to take into account, and what are the different approaches and things that people have been doing or have done for those specific problems. For example, how do you create your virtual worlds, right? Whether you do it via artists or you do it via cloning the real world, etc. The same as how do you generate the scenarios? What are you testing in the first place, right? Because depending on how you define that, your system will be able to do certain things versus not. We will be looking at things like the virtual world dynamics, right? The way that actors interact, as well as the way that the self-driving vehicle behaves in the real world. And then things like sensor simulation will be some of the other things that we'll be covering today, as well as hardware in the loop. This is something that typically is employed a lot in industry, which is, you can't just test everything in software. You're going to have specific hardware, compute, etc. And then you want to make sure that when you're testing, the level of fidelity of your simulation blocks becomes better and better and better, right? So in this, B&B approach that I was talking about, you want to make sure that the level of complexity of your testing increases, but every one of your subtests gives you as much information because it's super high fidelity as possible. So you decompose, combine, and then you kind of break the combinatorics of the entire problem. Just think about, how many things and how many variations you have in the real world. So we will go over, some of these things with a really, really nice comprehensive simulation session. And last but not least, as I said, we have a new model this year in terms of systems, safety, and V&V, right? Validation verification, where we were looking at, we'll give you just a flavor what this is. And this is something that is, is very exciting, and at the same time, it's very different from what you will kind of learn as a computer vision or machine learning person. But it's something that you really need to understand well so that you build the right technology. So we were looking at things like, what does it mean safety, even from a culture perspective, engineering perspective, functional safety, product safety. How do you make your arguments when your system is actually safe to deploy in the real world? And, we will be, talking about coverage, things like this, and how you can use simulation, for example, to make your safety case argument. Okay, so we will give you, it will be a short session. We can go for hours on this, but we just want to give you kind of a flavor of what you need to do as well when you're actually not just building cool tech, but you're actually building a real product in the real world. All right, and with this, that's it for my first session. Hope you have a great tutorial. And now I guess Andre is going to tell you all about hardware and sensors. Andre.